Okay, normal distribution. All kinds of things can be put on a normal distribution curve like this here. When things are very symmetrical, the data is very symmetrical, sometimes we'll assume that it has normal distribution or approximates normal distribution, so that we can make certain assumptions about the breakdown of how the data is put together. Helps us understand it faster, kind of like a box and whisker plot in a way. A normal distribution is modeled by a bell shape, so you get this bell-shaped curve here. It's called a normal curve. It is symmetric about the mean. Okay, the mean we abbreviate as x bar. Sometimes in certain statistics you'll see the mean also listed as mu, which looks like a fancy lowercase u for mu, but I will try to use x bar. And the standard deviation. So the total area under the curve is 1 or 100%. 100% of the data must be reflected in the curve. And here's the breakdown as we move away from the mean right here. As we move away from the mean, counting by standard deviations. So the mean plus a standard deviation, the mean plus 2 standard deviations, the mean plus 3 standard deviations. Going backwards, the mean minus a standard deviation. I promise this will make more sense when we put more numbers in here and to understand it better. The mean minus 2 standard deviations and the mean minus 3 standard deviations. What this is saying is that the mean and the median would be the same, since this is symmetric. So from the mean and below, 50% of the data must be. From the mean and above, 50% of the data must be. And 100% of the data has to be under the curve completely. If I look at just a section, if I go to the mean plus a standard deviation, that is reflected by this area right here. Between the mean and 1 standard deviation above the mean, 34% of the data exists. If I go the other way, between the mean and 1 standard deviation below the mean, again, likewise, 34% of the data must exist. So if I look between 1 standard deviation above the mean and 1 standard deviation below this total shaded area, it must be 34 plus 34, or 68% of the data. It's a little easier to see on this next slide here. Perhaps. So what it is we just discussed here was if I go 1 standard deviation below and 1 standard deviation above, that would be indicated by this purple line here, where you would add the 34% and the 34%. That gives you 68% on 1 standard deviation, plus or minus from the mean. If I go out an additional standard deviation, 13.5% of the data exists between 1 standard deviation and 2 standard deviations. So likewise, that must match on a similar portion of the curve here. So if I want to know how much data is between the mean and 2 standard deviations below, and the mean and 2 standard deviations above, I add all these percentages together. 34 and 34 is 68, plus 13.5 and 13.5 should give me 95%. Continue this experiment out one more. Between 2 and 3 standard deviations below the mean, 2.35% of the data exists right here in this next to last section. If I go to the same section over here between 2 and 3 standard deviations above the mean, 2.35% of the data exists here. So if I want to know how much data exists between the mean and 3 standard deviations below it, and the mean and 3 standard deviations above it, I would add up all these percentages here that are in orange. Or I could take the 95% that I already knows there and add the 2.35 and the 2.35, and that would give me 99.7. An alternate way to get here, and I think it's a little faster, is I'm pretty much looking at, when I'm looking at the orange part, I'm looking at the whole curve, everything, except for this last little bit here at the end. I'm not using that, and I'm not using that. So 100% minus 0.15 and 0.15 put together. It's going to be minus 0.30. That will also give me 99.7%. All right. We're going to get very used to drawing these curves and labeling them with their percentages and the mean and the standard deviations. First example here, part A, normal distribution has mean of x bar and standard deviation. For a randomly selected value of x from the distribution, find the, we got to understand this, the probability that a piece of data is between the mean and 3 standard deviations above the mean. So the mean plus 3 standard deviations. So I would go to my graph, I would draw me a curve, and I would label it like it's labeled down here where the mean is in the middle. So the mean is in the middle, x bar. Mean plus the standard deviation, plus 2, plus 3. Then go backwards, the mean minus the standard deviation, minus 2, minus 3. Lay in all your percentages. Some of mine are already here. I'm going to move around the rest of them. So I got 34% here. So 34% must be here. I got 13.5% here. So I must have 13.5% here. I got 2.35% here. I must have 2.35% here. I got 0.15 here. So I must also have 0.15 here. Now that it's fully labeled, this example is already kind of partially done for you. I would go between the mean and 3 standard deviations above the mean. So here's the mean, and here's 3 standard deviations above the mean right here. So I'd be looking at this blue shaded area that I'm shading in red now. So I want to know what is the probability that any randomly selected piece of data exists in the shaded range that is between the mean and 3 standard deviations above the mean. In order to find that out, I add the percentages. 34 plus 13.5 plus 2.35. So I add all those up, and here we go. Probability that a randomly selected piece of data falls between the mean and 3 standard deviations above the mean, if I can get my pencil to work right, is 0.4985. Okay. An alternate method of getting there is once I was looking on my graph, I basically had almost everything highlighted from the mean over except for that last little section, which is 0.15. So I could have gone 50 minus 0.15, and I would have gotten the 0.4985. That's a probability. It's written as a decimal.